Hi, my name is Erin Fallon, and today we're going to be discussing ocean deacidification technology. First, we're going to go through ocean acidification, the reality of it, the causes, the chemistry behind it, and the effects. Then we're going to jump into the technology and the possible solutions. Before I begin, I'm hoping as educated biochemistry students, we all believe in global warming and we all understand global warming. If you do not believe in global warming, I'm sorry, this may not be the presentation for you. To begin, the reality of ocean acidification. Carbon pollution since the Industrial Revolution. Carbon pollution has been affecting the climate in an increasingly negative manner. Greenhouse effects. As the atmosphere becomes more carbon-rich, more and more heat is trapped. The greenhouse gas effect causes the atmosphere to absorb infrared radiation from the sun, and this prevents the Earth from refracting it back into space. Greenhouse gases include methane, carbon dioxide, ozone, nitrous oxide, and chlorofluorocarbons. Acidifying our oceans. Carbon pollution isn't just warming our climate, it's acidifying our oceans, causing oceans to acidify faster than they have in 300 million years. Ocean acidification has already reduced the pH of the oceans by 0.1 units. This is roughly a 30% increase in acidity levels since the pre-industrial era. The causes. High concentrations of atmospheric carbon dioxide, essentially burning fossil fuels. Every day, 22 million tons of carbon dioxide from factories, cars, and power plants are absorbed by the world's oceans, and this is only a fraction of what we are putting in the atmosphere every day. The chemistry behind ocean acidification. Carbon dioxide in seawater. When carbon dioxide is added to water, carbonic acid is produced. This is reduced to bicarbonate and hydrogen ions. Carbonic acid lowers the pH by giving up a proton. This is simple acid-base chemistry, and we're all upper-level biochemistry students, so I'm not going to get too in-depth. Seawater contains three major groups of dissolved inorganic carbon: dissolved carbon dioxide, bicarbonate, and carbonate ions. The buffer system. The addition of CO2, resulting in carbonic acid, reacts with available dissolved calcium carbonate and forms bicarbonate ions. This is very important to remember for future slides, as calcium carbonate will be relevant to marine ecosystems we're going to look at later. The blood buffer system. I wanted to bring up the blood buffer system since we spent a lot of time going over it in this course, and there are a lot of similarities between the blood buffer system and ocean acidification, as both are based on dissolved CO2 in solution. So as we know, the healthy pH of blood is 7.35 to 7.45. Greater than 7.45 leads to blood alkalosis, and less than 7.35 leads to blood acidosis. And I just want to make a point of saying that this is the same for the oceans. Too acidic or too alkaline, and organisms can't properly function. As we know, neither is healthy. You have to stay in that healthy range, or this can lead to death. Blood contains large amounts of carbonic acid, a weak acid, and bicarbonate, a base. Bicarbonate neutralizes excess acids in the blood, while carbonic acid neutralizes excess bases. This equilibrium between the weak acid and its conjugate base is known as the blood buffer system. In the bottom of this page, I've included a figure, a titration curve, just to sort of trigger everyone's memories, and then I included the equation written out of the blood buffer system. Now the effects of ocean acidification. Increasing bicarbonate increases ocean acidity, which drives chemical reactions towards the undersaturation of seawater with calcium carbonate. Calcium carbonate is an essential compound for many marine organisms to form shells and skeletons, impairing their survival. Some of these organisms include oysters, clams, sea urchins, coral, and plankton, and none of these can maintain a healthy structure without it. In removing excess hydrogen ions produced by carbonic acid, carbonate, an essential component of calcium carbonate, as I've said, forms the bicarbonate ion. This leaves excess calcium and limited carbonate for calcium carbonate-dependent organisms. Acidic water makes it harder for them to grow and maintain shells, and we are already seeing the effects of acidification as coral reefs collapse, oyster beds disappear, and plankton populations get smaller and smaller. This is just a diagram depicting what I've said. As the oceans absorb carbon dioxide from the atmosphere, they create waters richer in carbonic acid, and carbonic acid, quote-unquote, steals carbonate needed by some marine organisms for their shells. Coral reef collapse. Thousands of species are dependent upon coral reefs for their habitats, as I'm sure you all know. And acidification results in the reduction of skeletal density of reefs by 0.36% each year and a reduction of linear growth by 1.06% each year. This weakens reefs against hurricane-level storms, making them more susceptible to complete annihilation. On the right, I've included a picture of the Great Barrier Reef after a hurricane, and as you can see, it's been decimated due to its lacking structural needs, and it wasn't able to withstand the effects of the storm. This, on top of coral bleaching, due to the rise in oceanic temperatures, another factor of global warming with ocean acidification, leads scientists to believe we will lose most reefs in the next decade. On the left, I've included a picture of a reef in 1976 and 2016 as a comparison, and you can see the effects of bleaching and just the absolute annihilation of this reef. Effects on food chains. Food web interruption. Plankton are the primary food source for the majority of the world's oceans. On the right, I've included an image to show that plankton rely on calcium carbonate for their calcified structure. Without a strong base, the upper levels of the food chains will crumble. Starvation. Loss of primary producers will result in a massive decline of all marine species. I'm sure we've all heard of bottom-up effects, so this shouldn't be too surprising to anybody. If the bottom of the pyramid crumbles, the entire thing will collapse. Human life and how it will affect us. Less marine life for human consumption due to starvation of marine species. Globally, fish provide more than 1.5 billion people with almost 20% of their average intake of animal protein, and nearly 3 billion people with 15% of that protein also results in a disruption of our global economy due to the lack of fishing and fisheries income. I actually recently read a statistic that suggests by 2030, 50% of the US population will be run by small businesses, and much of that includes farming and fishery-based businesses. So if we run out of fish populations, fisheries are really going to suffer in the coming decades. Possible solutions. Now that you know the problems, excess carbon dioxide, acidification in our oceans, and loss of marine life and ecosystems, we can talk about the solutions.